This is the video notes for 9.4, Rocking the Residuals. The correlation coefficient, which is what we've been learning about from lesson 9.1, is not the only tool that statisticians use to analyze whether a line is a good model for the data. They also consider the residuals. The residuals are the difference, so I'm going to highlight this. The difference between the observed value, the data, and the predicted value, the y value on the regression line. So it's just a simple subtraction. This sounds a little complicated, but it's not really. The residuals are just a way of thinking about how far away the actual data is from the regression line. So we're going to learn how to calculate residuals today. So we start with some data. Here's our table of data, x and y values, and we create a scatter plot and graph the regression line. In this case, here's the scatter plot, right? And the line of best fit or regression line turns out to be y equals 3x plus 6. Finally, to find the residuals, you draw a line from each point to the regression line as shown below. And I'm going to highlight those. Some of them are a little bit harder to see. So let's zoom in. This is the distance right here between the actual data point and the regression line. Here we go. Here's another distance between, or difference between, the actual data point and the regression line, the line of best fit. These are all the residuals right here, these distances. Okay. And ideally, you want these to be small, right? Because that means the regression line fits the data very well. We have a really high correlation coefficient, close to 1 or negative 1. So that's the ideal. So let's go ahead and learn how to calculate residuals. So let's turn the page. The residuals are the lengths of each of those segments. How can you calculate the length of each segment to get the residuals? So we're going to break this up into 2 steps. Okay. So the first step to find the residuals. So first step is to find the y value. Here, let me fix this really fast. So find the y value of the point that would be on the regression line. And remember, regression line is just the line of best fit, right? Okay, so you do that first. Once you find that y value of the point that would be on the regression line, you keep the same x value, but you find what that y value would be. Then all you do is a subtraction. Subtract that y value from the original y value of the data point, from the data point y value. Okay, and we're going to demonstrate this next. Okay, so that's the 2 steps in order to calculate residuals. So let's go ahead and test it out. Generally, if the data point is above the regression line, the residual is positive. If the data point is below the line, the residual is negative. Knowing this, use our plan from problem 1 to create a table of the residuals using each data point. Okay, so we're going to put in our x values. Okay. We've got 1, 2, 3, 4, 5, 6, and then we're going to put in our y values. 10, 13, 7, 22, 28, and 19. These x and y values are just coming from the table on page 215. So they're just from the previous page. Okay, now that we have that, we're actually going to calculate what the y value would be if it was on the regression line. So I'm actually going to, in this box right here, I'm going to write y value on, and the equation of the regression line is y equals 3x plus 6. Okay, and in order to find that, I'm going to take each of the x values, those do not change, and I'm going to plug them into the equation y equals 3x plus 1. So my first y value on that regression line is going to be 3 times 1 plus 6, so it's going to be 9. Okay, and I'm going to go really quickly to the previous page and show you where that would be located. So that's this point right here on the regression line. And then we're going to find this one next, and this one next, and then this one, this one. Do you see how we're just finding the points on the regression line at those x values? So x values do not change, but we will calculate all those y values. Okay, so let's do our next one. So this will be 3 times 2 plus 6. So that gets us 12. And then 3 times 3 plus 6 gets us 15. And then we do 3 times 4 plus 6, 18. 3 times 5 plus 6, that is 21. And then 3 times 6 plus 6. And that gets us our final one of 24. Now, the very last thing, according to number 1, is to subtract those y values from the data point y values. So that is what we'll do next. So this will be our residuals. So residuals. Okay, so our first subtraction is going to be our actual minus our y value on the regression line, right? 10 minus 9, so that gets us a residual of 1. Then we just go down the line, we'll do all our subtractions. 13 minus 12, a residual of 1 again. Then we're going to go 7 minus 15, a residual of negative 8. Then we go 22 minus 18, a residual of 4. This one is 28 minus 21, residual of 7. And then finally 19 minus 24, which is a residual of negative 5. Okay, so what we're seeing is how far away each of those original data points are from the regression line or line of best fit. Now, once we've done that, statisticians like to look at special graphs called residual graphs to judge their regression line. How did we do? Now we get a chance to do that. So we're going to graph the residuals from question 2. So when x is 1, our residual was 1, right? So we're just going to put a point right here at 1, 1. This is graphing the x value and the residual. That is what we just graphed, okay? And then at 2, our residual is also 1, so put it there. At 3, our residual was -8, so it goes all the way down here. A little bit lower, I think. Yeah, a little bit lower. Okay, at 4, our residual is, let me zoom out a tiny bit, 4, so that's all the way up here. At 5, our residual is 7. And then at 6, our residual was -5 right there. So that is what our residual plot would look like. Okay, so now let's answer a few questions about what we're seeing. So let's turn the page. Now that you've constructed a residual plot, think about what the residuals describe and answer the following problems. So let's see. First question, number 4. If a residual is large and negative, what does it mean? Okay, so let's look at that. Residual is large and negative, kind of like this one over here, like this -8, right? It means that the actual data point is far below the regression line and might be an outlier. All right, let's write that in. It means the actual data point is far below the regression line and might be an outlier. Okay, next one. Number 5. What does it mean if a residual is equal to 0? All right. If a residual is equal to 0, it means that that data point is actually right on the regression line. They intersect each other. It means the data point and regression line intersect. Okay. Number 6. If someone told you that they estimated a line of best fit for a set of data points and that all of the residuals are positive, what would you say? Yeah, if all their residuals are positive, what does that mean? That means all the data points, the actual data points, are above the line of best fit. Okay, so I would say that their line of best fit is too low. Right? Because if the residuals are all positive, that means that all the data points are above the regression line, above the line of best fit, and they have not done a good job of creating their line of best fit. It did not go through the middle of the data. Their line of best fit is too low and must be below all the data points. They'd probably have to redo their line of best fit, I imagine. All right, number 7. If the correlation coefficient for a data set is equal to 1, what will the residual plot look like? Well, the correlation coefficient is equal to 1. That means all the data points, all the dots are lining up in a straight line and would be right, they would all be intersecting the line of best fit. So what will the residual plot look like? On the residual plot, all the residuals would be 0. Let me zoom in a tiny bit. All the residuals would be 0. The reason is because all the data points fall on the regression line. All right, the next activity that we're going to do is look at residual plots and see if we can tell what's going on, right? We're just going to make some observations. Okay, so let's go ahead and turn the page. Number 8. Statisticians use residual plots to see if there are patterns in the data that are not predicted by their model. What patterns can you identify in the following residual plots that might indicate that the regression line is not a good model for the data? Based on the residual plot, are there any points that may be considered outliers? Okay, so we're looking for patterns and we're looking for outliers. So looking at number 8, I really like this part of the graph. This part of the graph is actually, to me, looks like our line of best fit. Our regression line is going through the middle of data. We have a kind of a nice even above and below for the residuals. So this area would honestly be a good linear model. Good linear model. As you head to the right in this residual plot, do you see how it's kind of spreading out more? So this section over here isn't as great of a linear model. It has more spread. Data starts to spread out. I don't really feel like there are any outliers. Possibly this very last one here on the bottom. That's at, I want to say it's at like 14, negative 14. It's at positive 12. It's kind of further away, but you'll see in a moment that there are examples where it's more obvious where there's an outlier. All right, let's move on to number 9. Let's see what patterns we're looking for and any outliers. So over here, we actually have a curved pattern going on. Do you see that? Kind of have a curved pattern going on. Curved pattern. So this is not a good one for a linear model, probably. Pattern. Rather than doing a linear model, maybe we would want to do a different one, right? A different model. Don't use a linear model here. So we would want some kind of curved model, maybe exponential or quadratic, something that would take into account this curved pattern that we're seeing. All right, let's look at the residual plot for number 10. So number 10, what are we seeing here? So this one is very interesting because the residuals are alternating positive and negative. Do you see that? Positive and negative, positive, negative, positive, negative. So I wonder if this one is maybe not so good for a linear model, maybe something else. Maybe this is some kind of trig model here. So residuals, alternate, negative to positive. Maybe some other model would be good here, like some kind of sine wave or cosine wave, something different, right? All right, let's look at our last one, number 11. So here, do you see how it's pretty obvious that there is an outlier here? Look at this one over here. I would definitely consider this an outlier, where we really haven't had one that's obvious so far. And then the rest of this looks pretty nice as a linear model. Do you see that? It's our line of best fit going through that middle. The data points are pretty evenly above and below. Okay, so here's a comment about when to decide whether a linear model is good. So I'm going to put that over here. An ideal residual plot for a linear model looks like this. We have randomly spaced residuals, but they're close to this x-axis right here, which is what's going on in this one, right? So here's our x-axis. Right there. And they're randomly spaced, but they're still fairly close to that axis. Okay. Randomly spaced residuals close to x-axis. Okay. All right, those are our examples of residual plots. Let's go ahead and move on to our takeaways. So in our takeaways, we've got this Venn diagram that we're going to fill in with what we've learned about correlation coefficient and residuals. So let's fill in the middle first. So where it says things that both the correlation coefficient and residuals tell us, the main thing that both of them tell us is if, let me zoom in a tiny bit more, if a linear model fits the data. Okay, so that is what both of those attributes tell us. The correlation coefficient and residuals tell us if a linear model fits the data. So let's go over here to the left. What do we learn about the data just from the correlation coefficient? Okay, so we learn direction, right? Is it positive or negative? And we also learn strength of the linear relationship, of the linear relationship. Okay, and so the strength can be described as strong or weak or no linear correlation. Okay. All right, let's look at what we learn just from the residual plot. Okay, so that's our right. What we learn about the data from the residual plot. Okay. First thing we learn is how far apart, not apart, but how far the data is from the predicted value, right? The predicted value is the regression line. We also learn if there are possible outliers, okay, which we did not get from the correlation coefficient. And the third thing that we learn from a residual plot is patterns that suggest a different model. Okay, so maybe we're not seeing patterns that look like a linear model will work. Maybe instead quadratic or exponential or trigonometric would work better, where we've got some kind of curve going on as opposed to a straight line pattern. Let me add a tiny bit more. Patterns that suggest a different model might work better than linear. Okay. In this lesson, we learned that a residual shows the difference between the y value of a data point and the predicted y value on the regression line or line of best fit. We calculated the residual values and used residual plots to evaluate whether a linear model is appropriate for the data. I hope that this helps you, and I wish you best of luck on your practice.